Welcome back, students. Today in this session we are going to study chapter number 10, circles. So in this chapter we are going to study some of the theorems related to circle. So before starting those theorems, we will do a quick review of what is a circle and its related terms. So the definition of the circle says the collection of all the points in a plane which are at a fixed distance from a fixed point in the plane is called a circle. So according to the definition, if I take this as the fixed point, and these are the collection of all the points which are at a fixed distance from that particular fixed point, then this collection of all the collection of all these points is called a circle. So the collection of all the points in a plane from a fixed point which are at a fixed distance is called a circle. The fixed point is our center, that is center of the circle. The fixed point is the center of the circle, and the fixed distance, that is, this will be the fixed distance. This fixed distance is the radius of the circle. Now this circle divides the plane on which it lies into three parts. That is the part which is inside the circle, which we call as the interior of the circle, and the part on the circle, which is the circle, and the part which lies outside the circle, which is called the exterior of the circle. Now let us see what is a chord. If I take 2 points on the circle, that is point P and Q, point P and Q on the circle, then the line segment joining these 2 points is called the chord of the circle. This line segment is known as the chord of the circle. So the line segment which both ends lie on the circle are called the chord of the circle. So the diameter of a circle will be the chord passing through the center. So the diameter of a circle is the chord passing through the center of the circle, and we all know that the diameter is twice the radius of the circle. Next, we will study about arc of an circle. Again, let us consider 2 points on the circle, that is point P and Q. So these 2 points P and Q divide the circle into 2 pieces. So each pitch of a circle between 2 points is called an arc. So there are 2 arcs, that is major arc and the minor arc. So the larger piece, that is the larger piece of the circle, that is this part, is called the major arc, and the smaller piece divided by these 2 points, that is this piece of the circle, is called the minor arc of the circle. We will represent it by the, say suppose this is a point R on the major arc, then we will name the major arc as P R Q and the minor arc as P Q. Next is the circumference of a circle. The length of the complete circle or the perimeter of the circle is known as the circumference of the circle. Now let us study the term segment. So segment of a circle. Let us consider these 2 points P and Q, and if I draw a chord here, the chord PQ, this chord divides the circle into 2 parts, that is this part and this part. So its region is called the segment of a circle. The bigger region is called the major segment, and the smaller region, that is this one, is called the minor segment. This is minor segment. Minor segment. So the region between a chord, is called the segment of a circle. Next, let us study about the sector of a circle. So what is the sector of a circle? Consider these 2 points P and Q on the circle. So PRQ will be the major arc and the PQ will be the minor arc. So if I do two radii PO and PQ, then OQ, then the circle is divided into two regions. There is the region here and this smaller region. So the region between an arc and the radii and the two radii joining the center to the end points of these two arcs are called the sector of the circle. The bigger region will be the major sector. This will be the major sector, and the smaller region, this will be the minor sector of a circle. So these are some of the terms which are related to circle. Now we will study some of the theorems given in your books relating to this chapter. So the first theorem given in your book is theorem 10.1, which says equal chords of a circle subtend equal angles at the center. So let us try to understand what this theorem says. So here is a circle with center O, and AB and CD are two equal chords. That is, AB is equal to CD, and these are two equal chords of the circle with center O. So the theorem says equal chords of a circle subtend equal angles at the center. So AB and CD are the equal chords. Now the angles subtended by these two chords at the center, there is this angle AOB and another angles subtended by the chord CD, there is angle COD, will be are of equal measure. That is, measurement angle AOB will be equal to the measurement angle COD. So the theorem says these two angles at the center subtended by the equal chords AB and CD will be of equal measure. You can easily prove this theorem by proving that triangle AOB and COD are congruent to each other using the SS congruence rule. Next is theorem 10.2, which is the opposite of theorem 10.1, and it says if the angles subtended by the chords of a circle at the center are equal, then the chords are equal. So there is a circle with center O, A, B, and C, D are the two chords subtending an equal angle at the center. There is angle AOB. Angle AOB is equal to angle COD. Then, according to the theorem, then these two chords are of equivalent length. That is, AB equal to CD. If angle AOB is equal to angle COD, then the two chords AB and CD are of equivalent length. Next is theorem 10.3, which is that perpendicular from the center of a circle to a chord bisects the chord. So let us try to understand this theorem. So according to the theorem, here is a circle with center O and AB is a chord. Now if I draw a perpendicular from the center of the circle to the chord, then it bisects the chord. So AM will be equal to BM. So the line perpendicular from the center of a circle to the chord bisects the chord. Next, theorem 10.4, which says the line drawn through the center of a circle to bisect a chord is perpendicular to the chord. This is the converse of theorem 10.3. So if I draw a line OM which bisects the chord AB, that is, if AM is equal to BM, then the measure of this angle will be 90 degree. Then angle OMB will be 90 degree. This is the converse of the previous theorem. Next is theorem 10.5. There is one and only one circle passing through three given non-collinear points. So PQR are three non-collinear points. Then there will be only one circle passing through these 3 points PQR. One and only one circle. Next, theorem 10.6, which is equal chords of a circle are equidistant from the center. So this is a circle with center O, and let us take two chords which are of equal in length. So chord AB and chord CD are two chords on the circle. Two chords of the circle which are of equal length or are of equal chords. So AB is equal to CD. They are equal chords. Then the theorem says both the chord will be of equidistance from the center. That is, they will have the same distance from the center. So OM will also be equal to OM. So if the two chords AB and CD are of equal in length, then they are of equidistance from the center. So if AB is equal to CD, then OM is equal to ON. That is, the two chords are equidistant from the center. Next is theorem 10.7, which says chords equidistant from the center of a circle are equal in length. This is the converse of theorem 10.6. So this AB and CD are two chords. So according to the theorem, if OM is equal to O, and that is, the two chords are equidistant from the center O, then the two chords will be of equal in length. Then AB will be equal to CD. Next is theorem 10.8. Theorem 10.8 says the angle subtended by an arc at the center is double the angle subtended by it at any point on the remaining part of the circle. So let us try to understand this theorem. So here is a circle with center O, and P and Q are 2 points on the circle which divides the circle into two arcs, that is major arc PQ and the minor arc PQ. So the theorem says the angle subtended by an arc at the center. So this arc PQ subtend an angle at the center, that is, this angle POQ is double the angle subtended by it at any point on the remaining part of the circle. The remaining part of the circle will be this one. There is this major arc. So this PQ, let us say this PQ subtend an angle PRQ on the remaining part of the circle. Then according to the theorem, then measurement angle POQ POQ will be equal to twice the measurement angle PRQ. So I'll repeat, the theorem says the angle subtended by an arc, the angle subtended by an arc at the center, that is this angle, is double the angle subtended by it at any point on the remaining part of the circle. So measurement angle POQ will be twice the measurement angle PRQ. Suppose if this POQ measurement angle PRQ, suppose angle PRQ is of measure 60 degree, then the measurement angle POQ will be twice that of PRQ, that is 120 degree. Next is theorem 10.9 and 10.10. First of all, theorem 10.9. 10.9 says angles in the same segment of a circle are equal. So this point P and Q divides the circle into two segments. For example, this major segment and the minor segment. So this point P and Q on the circle divides the circle into two segments. So the theorem says angles in the same segment, let us suppose this angle PAQ be one of the angle and angle PBQ be other angle. So this two angle will be of equivalent measure because they lie in the same segment. So angle PAB will be equal to angle PAQ will be equal to PBQ. So angles lying in the same segment of a circle will be of equivalent measure. For example, you can say this angle PCQ also lie in the same segment, so this will be also equal to, these three angles will have equal measure. Here one of the important topic is that angle in a semicircle is 90 degree. That is, angle in a semicircle is a right angle. For example, here angle LMN, the measure of this angle LMN will be equal to 90 degree because these angles lie in a semicircle. This Ln is the diameter, so the diameter divides the circle into two equal halves, that is, each half is known as the semicircle, and the angles in a semicircle is a right angle. Now moving on to the theorem 10.10. The theorem 10.10 says if a line segment joining 2 points subtends equal angles at the other points lying on the same side of the line containing the line segment, the 4 points lie on a circle. This is the converse of the theorem 10.9. So if a line segment joining 2 points, that is point P and Q, on the circle subtend equal angles on the at two other points lying on the same side of the line containing the same segment, that is angle PAQ and PBQ are equal if PAQ and PBQ are equal, then the 4 points, that is P, A, B and Q, and the points P, Q, A and B lie on the circle. Lie on the circle. This is the converse of the theorem 10.9. Next is theorem 10.11 and 10.2. So in theorem 10.11 it says the sum of a pair of opposite angles of a cyclic quadrilateral is 180 degree. So here the cyclic quadrilateral means it is a type of quadrilateral in which all the four vertices of the quadrilateral lie on the circle. For example, this is circle with center O. If I draw a quadrilateral here with all its vertices lying on the circle, then this quadrilateral will be a cyclic quadrilateral. So here the quadrilateral ABCD is a cyclic quadrilateral. So the theorem says the sum of a pair of opposite angles of a cyclic quadrilateral is 180 degree. That is, the opposite angles of a cyclic quadrilateral add up to 180 degree. That is, angle A plus angle C is 180 degree, and angle B, this angle B and this angle D add up to 180 degree. So the opposite angles of a cyclic quadrilateral are 180 degree. In theorem 10.12 it says if the sum of a pair of opposite angles of a quadrilateral is 180 degree, then the quadrilateral is a cyclic quadrilateral. This is the opposite of the theorem 10.11. So if angle A plus angle C equal to 180 degree, or angle B plus angle D equal to 180 degree, then the quadrilateral will be a cyclic quadrilateral. Then the quadrilateral ABCD is a cyclic quadrilateral. Cyclic quadrilateral. Now let us solve questions from exercise 10.1. So first question is fill in the blanks. Question number 1. The center of a circle lies in the blank of the circle, that is, this is interior of the circle. A point whose distance from the center of a circle is greater than its radius lies in the exterior of the circle or interior of the circle. The point that will be which is greater than its radius will be outside of the circle, so this will be the exterior of the circle. The longest chord of a circle is this is the diameter of the circle. An arc is a blank when its ends are the ends of a diameter. When it is the ends of a diameter, the arc will be a semicircle. This will be semicircle. Segment of a circle is the region between an arc and blank of the circle. The segment of a circle is the region between an arc and the chord of the circle. A circle divides the plane on which it lies into three parts, that is interior, exterior, and the circle. Write true or false, give reason for answer. Question number 2. So the first statement is line segment joining the center to any point on the circle is a radius of the circle. This is true. A circle has only finite number of equal chords. This is false. We can have as many as infinite number of chords, equal chords. If a circle is divided into three equal arcs, it is a major arc. This is false. A chord of a circle which is twice as long as its radius is a diameter of the circle. This is true because the diameter is twice the radius. Sector is the region between the chord and its corresponding arc. This is false. The sector is the region between the radii and its corresponding arc, not the chord. A circle is a plane figure. This is true. Next questions from exercise 10.2. Question number 2. Prove that if chords of congruent circles obtain equal angles at their centers, then the chords are equal. Exercise 10.2, question number 2, solution. So in the question it is given that there are two congruent circles with center O and O dash, and AB and CD are the chords on the circle with center O and with center O dash respectively, such that these two angles, angle AOB and angle CO dash D, are equal in measure, and we are to prove that the two chords AB and CD are equal in length. So proof. Proof in triangle AOB and triangle CO dash D, AO equal to CO and BO equal to BO dash, AO equal to CO dash and BO equal to DO dash. They are the radii of the congruent triangle, and angle AOB equal to angle CO dash D. This is given. Therefore, triangle AOB is congruent to triangle CO dash D by SAS congruence axiom rule. So if these two triangles are congruent, then we can say that the side AB is equal to CD, the side CD of the corresponding triangle. So these are nothing but the chords of the two congruent circles. Hence proof. Hence proof. Next, exercise 10.3. Question number 3. If two circles intersect at 2 points, prove that their centers lie on the perpendicular bisector of the common chord. So we are given two circles with center O and O dash. These two circles intersect at the point A and B. So AB will be the common chord of the two circles, and we are to prove that the centers of these two circles lie on the perpendicular bisector of this chord AB. So to prove AM equal to PM, and the measurement angle OMA is equal to 90 degree. These two will prove that the centers of the two circles lie on the perpendicular bisector of the common chord. So to prove this, let us construct. So in construction, let us join OA, OB, AO dash and BO dash. So let us join OA, OB, O dash A and O dash B. Now proof. In triangle, let us consider two triangles. That is, in triangle AO dash, AO dash, and in triangle BO dash. BO, thus we get AO equal to BO. That is, they are the radius of the same circle. And also AO thus equal to BO thus. These are the radius of the same circle. Then O thus are common to both the triangles. Now, therefore, triangle AO thus is congruent to triangle BO thus by SS congruence theorem. If these two triangles are congruent, then we can say that measurement angle O thus OA is equal to measurement angle O thus OB. That is, these two angles are equal. That is by corresponding parts of a corresponding congruence triangle. Next, again we will consider two triangles, that is triangle OAM and OBM. Now, in triangle OAM and in triangle OBM, we get OA equal to OB. That is, radius of the same circle and measurement angle AOM is equal to measurement angle BOM, which we have proved here earlier. And then OM equal to OM. That is the side common to both the triangles. Now, by SAS congruence theorem, these two triangles are congruent. Therefore, triangle OAM is congruent to triangle OBM by SAS congruence theorem. Now, since these two triangles are equal, we can say that, let me write here, we can say that AM is equal to BM. AM is equal to BM. That is, we have proved the first part. Now, again, angle OMA, we can say that OMA is equal to angle OMB. That is, these two angles are equal in measure. This is the corresponding part of the congruence triangle. But we know that angle OMA plus angle OMB is equal to 180 degree. That is, these two angles forms a linear pair. This implies measurement angle OMA plus measurement angle OMA is equal to 180 degree. That is, OMB is equal to OMA. This implies twice the angle OMA is equal to 180 degree. This implies angle OMA is equal to 180 degree by 2, that is 90 degree, which proves the second part of what we are going to solve. So hence, let me write this as equation 1 and this as equation 2. Hence from 1 and 2 we can say that from 1 and 2 we can say that the centers of the two triangles, that is the centers of the two triangles, lie on the perpendicular bisector of the common chord AB, of the common chord AB. Or of the common chord of the both the triangle. Hence proof.